Hello everyone. So once we are done with the clock net shielding, the next step is to do a quick timing analysis with the real clocks. Since now we have the clock tree in place, so everything, the timing will change and everything seems to change over here because we are introducing a new logic over here which was not present as a part of your netlist. Okay, so with this new logic introduced, it makes sense to do a round of timing over here to check what is the current timing scenario. Okay, so what we'll do is we'll take this, let's say we take this particular data path. Okay, and we had already timed this particular data path. Basically we had found the combinational logic delay for this particular data path, which was theta. Next step is to find out the launch clock network delay, the capture clock network delay, and adjust these equations as per the launch and capture clock network delay. Okay, so in this case we have noted down over here delta 2 is the capture clock network delay, delta 1 is the launch clock network delay. So delta 1 looks like this. It's the real wire RC delay of this particular wire plus the buffer delay plus the real wire RC delay plus again this buffer delay and so on. It will go till the flip-flop 1 clock endpoint. Similarly for delta 2, it is the real wire RC delay plus the buffer delay plus next the real wire RC delay and so on. It will go till flip-flop 2. And in the combinational delay path, you have this clock to Q delay of flip-flop 1. You have the estimated wire delay. It's not the real wire delay, it's the estimated wire delay. You have the delay of this particular logic 1. You have an estimated wire delay between 1 and 2. You have the real delay of 2. You have the estimated wire delay of 2 and flip-flop 2. Okay, so combinational delay will be still consisting of the estimated parasitics. Clock network delay delta 1 and delta 2 will be the real parasitic delay. So once the clock tree is built, it's never touched in it's never touched in further optimization stage. So that's why it does make sense to do an amount of timing analysis at the clock tree synthesis stage. Okay, so the defining equations for setup becomes something like this. Your combinational delay plus launch clock network delay is should be less than the clock period plus the capture clock network delay minus the setup time minus the setup uncertainty. So everything remains the same as in case of the timing optimization or timing analysis that we did for placement stage, except that there are two new terms that gets added. One is the delta 1 and delta 2, that's the launch clock network delay and capture clock network delay. So we have talked about this defining equations and how do we derive this equation a lot in the clock tree synthesis videos. You might want to have a look into those videos. So the next step after we did a quick timing analysis of the clock tree synthesis, next step is to route the design. Okay, so we'll go with the route, and in this case route, now we will be actually getting access to real wires. So the route looks something like this. So basically now the wire, there is no more estimated wire. This is a real wire that we see over here. This is again a real wire that we see over here, and these routes are based on the connectivity from the netlist. Okay, so once we route this particular design, you see that a D in 3 is connected to flip-flop 1 based on the netlist connectivity. Okay, so you need to route the design and you need to maintain the existing timing scenario. For example, we did a timing analysis in the previous stage, in the clock tree synthesis stage. The route stage should make sure that while you route the design, we should not be deteriorating the existing timing scenario. We should not get worse than that. If we can improve it, we can improve, but we should not be going worse than that. That's the function of the timing of the routing engine. Okay, so by that what we mean is, for example, there was a timing scenario from flip-flop 1 to flip-flop 2 with the help of this clock tree. So the current route engine will make sure that the timing scenario during the CTS stage is not deteriorated. That's how the route has to be. Else what can go wrong? Let's say D in 1 to flip-flop 1, there is this route. Due to some reasons, if it routes in a different fashion, the complete wire estimated delay, the complete delay of this particular wire that we had estimated will not become true. Again, the same case for, let's say, the delay from 2 to flip-flop 2. If this route was not straight, but it went somewhere over here and then it came back to a flip-flop 2, we had the estimated wire delay that we had done, that might not match with the exact route delay. So it becomes a very necessary step for the router to make sure that the existing timing scenario or existing timing is not disturbed while we do routes. Okay, so this we'll talk a lot about route in the upcoming sections, where that section is completely dedicated to route. This is the overview of it. Next step after the route is to clean up the DRCs. So DRC are design rule checks. So for example, while routing, we see some placement, we see some spacing or shots. For example, if you look this area, this particular circle, whatever has been encircled over here, if you look into this area, these two routes are much closer to each other. So it might lead to a lot of coupling, and it might not even be able to able to get fabricated by a lab, by a foundry. So finally, this design has to go to a foundry to get fabricated, and foundry have their own rules. For example, one rule, what it says is the minimum spacing between two wires should not be some x micrometer. Okay, in this case, if it crosses x micrometer, for example, let's say it should not, just an example, if the foundry says, if the rule says that between two different routes the minimum distance should be 10 micron, for example, and over here if the distance is 5 micron, this will be flagged as a DRC violation, and it's called design rule check violation. So similarly, there is if you see this wire is going through this wire, so there is a short over here. So the signal which is supposed to go from flip-flop 1 to 1, it might interact with this particular net which is going to flip-flop 2 to buffer. So this should not happen because it's actually short circuiting your design. So these kind of checks are done in this particular stage, which is called DRC clean, and we'll be talking a lot about DRC clean in a separate section in the existing course. This is an overview of it. So this is what we did. This is what we do finally when we try to do a DRC clean. And there are other problems while we try to do DRC clean. For example, there had been, for example, with the existing route, there had been a timing estimation that had been done, but due to the DRC clean step, the routes might just move somewhere in other places and the wire estimation will change, and as a result of that the timing will change. So we'll talk about all this in the DRC step. This is an overview. So we have to do this step after we do a route. Okay, so next, after we have done with the DRC cleaning, the next step is to do a complete parasitic extraction. Okay, by complete parasitic extractions, because we have now the data path routes, we now have the clock routes, we have the shields, and we have everything in place. So it does make sense at this stage to do a full parasitic extraction. So the scenario, or the way it will look, like the way it will look is something like this. So the complete chip, it will be the resistance and capacitance of the entire chip will be extracted through some mechanism. They will be extracted, all the routes and everything will be extracted, and now you do a final round of timing analysis with the extracted spef. So there is now no more estimation, wire estimation. Now we have real wires, we have real parasitics. With that, we need to do a timing analysis, and we do a timing analysis which is the final timing analysis. And the way and the things that the final timing analysis looks are into the real clocks, the real clock wires, the real data path wires. Okay, so your timing equation will look something like this. For example, if we do a timing analysis for flip-flop 1 to flip-flop 2, the launch clock network delay remains the same, the capture clock network delay remains the same. Now your combinational delay, which is from flip-flop 1 to flip-flop 2, through this combinational logic, it will now have a real wire delay rather than the estimated wire delay what we have been doing till now. Okay, so your defining equations will look something like this. You have your combinational delay plus your RC wire. This is now the real wire delays between flip-flop 1 to 1, 1 to 2, 2 to flip-flop 2, and plus the remaining equations remains the same. Okay, so this is the final step of final stage of the physical design flow. There are again some intermediate steps like which are specifically industry oriented. We'll be talking about them when we will be going into further sections. So these were the few steps which will give you an overview of physical design flow. From next lecture onwards, we'll be taking one step and we'll be trying to explain them in more detail. For example, let's say define width and height of core and die. In the next set of videos, we'll be talking about how do we come up with the width and height of the core and die. What is the utilization factor? What is the aspect ratio? We'll come up with this. We'll start coming up with this particular terms, and we'll also go into detailed lectures for each and every step of the physical design flow from the next video. Thank you.